Hello everyone, my name is Yuekai Huang. I'm from Institute of Software Chinese Academic of Science. Today I will present our work, Characterizing and Predicting Good First Issue. As we know, the continuous improvement of an open source software project depends on the developer who contributed to it. But many developers may not be able to participate in an open source software project for a long term. In order to keep the volatility of open source software, newcomers are highly needed. On the one hand, many developers also eagerly participate in open source software projects, driven by multiple factors such as better job or enjoyment. On the other hand, there are many barriers which may hide the newcomers from self-onboarding. Specifically, newcomers often face the problem of not knowing where to start contributing to an open source software project, which prevents them from joining the open source community. To support newcomers, many open source projects utilize the good first issue label to mark the issues that are suitable for newcomers to solve. However, manually labeling GFIs is time and effort consuming given the large numbers of candidate issues. Therefore, we want to provide a thorough understanding of the characteristics of GFIs and an automatic approach in GFIs prediction. To achieve this goal, we mainly do two works based on GFIs from 10 popular open source software projects on GitHub. The first work is to characterize what makes a GFI. Specifically, we first collect 79 features which may exert the difference between GFIs and non-GFIs. These 79 features are mainly derived from three dimensions: clearness of issue description, complexity of change involved, and the skill required. The first dimension used to characterize GFIs is clearness of issue description. Ideally, GFIs should have a clear issue description telling what the problem was and where to make the changes, and it is measured by three categories of features. The first feature category is report appearance. We assume the issue report's appearance will influence whether the issues have a clear description, and this category contains four features. The second feature category is text richness. We assume the issues with rich texture description is more likely to specify the error to tackle and the change to make. And these categories contain five features. The third feature category is readability. The readability of the issues also reflects whether the newcomer can easily get the described problem and the required changes. And these categories contain 36 features. The second dimension used to characterize GFIs is complexity of change involved. We think the scope of the involved changes of the issue should be also considered, and the ideal GFIs should only touch a small part of code base, and it is measured by two categories of features. The first feature category is influence scope. We assume that the potential influence scope of GFIs should be as small as possible, and this category contains three features. The second feature category is code complexity. We consider that the involved code of GFIs should be as less as possible, and this category contains 8 features. Note that the features associated with code complexity can only be retrieved after the issue is closed. But in order to more comprehensively characterize GFIs and analyze its characteristics, we also extract these features. While in a subsequent classifier in established stage, we omit these categories of features and use the other categories of features to build the model. The third dimension used to characterize GFIs is skill required. Ideally, GFIs should only require limited skills so that the newcomers can manage to resolve them. And it is measured by two categories of features. The first feature category is issue types. We assume the type of the issues can potentially reflect how much appearance is needed, and this category contains 8 features. The second feature category is semantic. We assume the semantics involved in the textual descriptions of the issue indicate the required skills, and this category contains 15 features. After feature extractions, we categorize the GFIs with the hypothesis testing results about whether each of the aforementioned features exert a difference between GFIs and non-GFIs. Besides hypothesis testing for signifying the significance of the test, we also calculate the effect size of the test. The table on the right shows the number of significant features and the number of features with not negligible effect size. We can see most of the investigated features exert a significant and substantial difference between GFIs and non-GFIs, indicating they can be utilized for categorizing GFIs. Specifically, features related to the semantics, readability, and text richness of the issues play a large contributor in GFI's characterization. The second word is to propose an automatic prediction approach based on the extracted features. In detail, we compared four machine learning methods and selected the one with the highest performance for GFI prediction, and then explored the contribution of features to distinguish GFIs and also explore the influence of feature selection algorithms on performance. In predicting GFI traits, we put forward three research questions. One is, are the proposal features good at predicting GFIs? In this question, we aim to evaluate to what extent the proposal feature can predict the GFIs. The second is, what is the contribution of each categories of features in predicting GFIs? In this question, we examine the evaluated contributions of each categories of features in predicting GFIs, which aim at understanding these features. The third is, can a reduced feature set achieve comparable performance compared to the full feature set? In this question, we examine the performance when using feature selection algorithms which aim at providing actionable decision support for developers when choosing features in building GFI's prediction models. To answer research question 1, we conduct a 5-photo class validation on each project. Record each model's performance and treat the average values as a final performance of the project to avoid bias. We experiment with 4 common use machine learning algorithms to evaluate the GFI prediction performance, and use AOC to measure the performance of prediction models. We also adopt the metric PFG, which is defined as the percentage of true GFIs identified by inspecting the top K% issues predicted by the models for effort-aware evaluation. As we can see, among the 4 types of machine learning-based models, random variance models can outperform others with a median AUC of 0.88 and the PFG20 is 0.77. And then we compare the best models, that is, random forests, with the state-of-the-art baseline and a random approach. We can see that the performance of our approach is significantly higher than the 2 baselines, which further indicates the effectiveness of the proposal features in predicting GFIs. To answer research question 2, we use the same experimental setup as at research question 1. We first experiment with each category of features and obtain the performance of GFI's prediction, and then conduct experiments after removing each category of features from the 4 feature set. We can see that with any categories of features, the GFI's prediction performance is significantly lower than the performance used the whole set of the feature. Furthermore, when removing each category of features, the prediction performance will decrease. To answer research question 3, we experiment with 3 common use feature selection algorithms. Based on the previous hypothesis testing results, we additionally employed the other 2 feature subset choice. The sigfed, which means all the significant features, and the h-sigfed, which means all the features whose effect size is not negligible. We can see that compared with using all proposal features, no matter what feature selection algorithm is utilized, the performance would decline. At last, let me make a conclusion for our work. In this work, We propose 79 features from 7 categories of 3 dimensions to characterize the GFIs, and most of the features are significantly different between GFIs and non-GFIs. And features related to the semantics, readability, and text relations of the issue play a large contribution in GFI's characterization. And our GFI's prediction approach can achieve a median AUC of 0.88 with the proposal features, which significantly outperforms the state-of-the-art baseline. And in general, all proposal features are useful in predicting GFIs, and we recommend the practitioners utilize all features in model building. That's the end of my presentation. Thank you for your listening.